Tonight, we're diving into a question that has quietly haunted astronomers for decades, a mystery so profound that it challenges everything we thought we knew about planetary formation. How rare is the solar system we call home? Not just uncommon, not just unusual, but potentially so extraordinary that finding another one like it might be nearly impossible. The visuals are here to guide you, but there's absolutely no pressure to keep your eyes open. Feel free to let them drift closed, breathe deeply, and allow your imagination to float through the cosmic neighborhood we're about to explore. Sometimes the most profound truths about the universe reveal themselves when we're in that peaceful space between waking and dreaming. I'd love to know where you're joining me from tonight. Drop a comment with your location and the time where you are. There's something beautifully poetic about discussing the rarity of our solar system while we're all scattered across this pale blue dot, each experiencing this moment from our own unique vantage point under the same starlit sky that has watched over countless generations of cosmic wanderers. Picture this for a moment. You're standing in a cosmic library containing information about every planetary system in our galaxy. Shelf after shelf stretches into infinity, each book representing a different arrangement of planets around distant stars. As you walk through this celestial archive, you begin to notice patterns. Most books tell similar stories, variations on familiar themes. But then, tucked away in a corner you almost missed, you discover a single, extraordinary volume. Its pages describe something so unusual, so perfectly orchestrated, that it seems almost impossible. That rare book is the story of our solar system. What makes this tale even more remarkable is that we're not just reading about this cosmic rarity from the outside. We're living inside it, inhabitants of what may be one of the most extraordinary planetary arrangements in the entire Milky Way galaxy. Every sunrise you've ever witnessed, every sunset that's taken your breath away, every gentle breeze that's carried the scent of flowers or rain, all of these moments unfold within a cosmic configuration so improbable that it defies easy explanation. The story begins with our star, that brilliant golden orb that rises each morning with such predictable reliability that we rarely pause to consider just how special it truly is. Our Sun belongs to a stellar class called G-type yellow dwarfs, and here's where the rarity begins to reveal itself. Among the hundreds of billions of stars scattered throughout our galaxy, only about 10% share our Sun's classification. The vast majority of stars, roughly 73%, are red dwarfs, smaller and cooler than our Sun, creating vastly different conditions for any worlds that might orbit them. But stellar classification is just the beginning of our cosmic story. Yellow dwarf stars like our Sun possess a unique combination of characteristics that make them particularly suited for nurturing life. They burn steadily for billions of years, providing the consistent energy output that allows complex chemistry to unfold on nearby planets. They're massive enough to maintain stable fusion reactions, yet not so massive that they burn out quickly or produce dangerous levels of radiation. They exist in what astronomers call the stellar Goldilocks zone, not too hot, not too cold, but just right for supporting the long-term evolution of planetary systems. Yet even among these favorable stellar neighborhoods, our Sun stands out as unusual. For its age and location within the galaxy, our star contains an unexpectedly high abundance of heavy elements, what astronomers call metals. This metallicity anomaly, known as the G-dwarf problem, suggests that our Sun formed under special circumstances, possibly migrating from a different region of the galaxy, where such metal-rich conditions were more common. This enhanced metallicity wasn't just a cosmic footnote. It was crucial for the formation of the rocky planets we see in our inner solar system today. As we venture outward from our extraordinary star, we encounter the next layer of our system's rarity, its architecture. Astronomers have discovered that planetary systems can be classified into 4 distinct types based on how their planets are arranged. There are similar systems, where planets maintain roughly the same size throughout. There are anti-ordered systems, where planets actually decrease in size with distance from their star. Mixed systems show seemingly random arrangements of planetary sizes. And then there are ordered systems like ours, where planets systematically increase in mass as you move away from the star. 4 small, rocky worlds hugging close to our Sun. 4 massive gas and ice giants residing in the outer reaches. This ordered arrangement, this cosmic choreography of size and distance, represents the rarest class of planetary systems in our galaxy. When astronomers analyze data from thousands of exoplanets discovered by space telescopes, they found that ordered systems like ours make up less than 1% of all planetary configurations. But the rarity goes deeper than simple architectural classification. Our solar system contains 8 planets, a number that might seem arbitrary until you realize how extraordinary it truly is. Among the approximately 900 multiplanetary systems discovered so far, not a single one matches the structure or planetary characteristics of our solar system. While having 8 planets might not be impossibly rare in terms of pure numbers, the specific arrangement and characteristics of our 8 worlds create a configuration that appears to be absolutely unique in our current catalogue of known systems. Consider the delicate gravitational ballet that has maintained our system's stability for over 4.5 billion years. Most multi-planet systems show evidence of chaotic past events, planets with highly elliptical orbits that speak of gravitational disruptions, collisions, and ejections. Our solar system's nearly circular orbits represent a remarkable achievement of celestial mechanics, suggesting that our formation process was unusually gentle and well coordinated. This stability becomes even more remarkable when you consider the role of planetary migration in solar system formation. Current theories suggest that giant planets typically form far from their stars and then spiral inward through the protoplanetary disk, often ending up as what astronomers call hot Jupiters, massive worlds that complete their orbits in just a few days. These hot Jupiters, while rare at only 1% of all stars, represent a fundamentally different evolutionary path from what our system experienced. Our Jupiter, instead of becoming a hot Jupiter, appears to have undergone a complex migration pattern that astronomers call the Grand Tack model. In this scenario, Jupiter migrated inward toward the Sun, but then reversed course and moved back outward, possibly triggered by Saturn's formation and the gravitational interactions between these 2 giant worlds. This reversal had profound consequences for the inner solar system, clearing away much of the existing planetary material while leaving behind just enough for the formation of our 4 small terrestrial planets. The timing of this process was absolutely critical. Too early, and there wouldn't have been enough material left to form Earth and its siblings. Too late, and the inner system might have become crowded with larger worlds that would have prevented Earth from maintaining the stable, nearly circular orbit that has allowed liquid water to exist on its surface for billions of years. The precision required for this choreographed dance of planetary formation suggests that systems like ours require an extraordinary confluence of circumstances to arise. But our solar system's uniqueness extends beyond just the number and arrangement of its planets. We exist in a single star system, orbiting one solitary yellow dwarf, and this too is more unusual than you might expect. The majority of stars in our galaxy exist in binary or multiple star systems, locked in gravitational dances with stellar companions. These complex gravitational environments create challenging conditions for planetary formation and stability, often leading to planets being ejected from their systems or forced into highly elliptical orbits that are hostile to the development of life. Our Sun's solitary nature has allowed for the formation of those stable, nearly circular planetary orbits that have remained undisturbed for eons. This stellar isolation is a crucial but often overlooked factor in our solar system's habitability and long-term stability. In a universe where most stars have companions, our cosmic loneliness becomes another mark of distinction. As we continue our exploration of this remarkable planetary arrangement we call home, each new layer of understanding reveals just how extraordinary our circumstances truly are. We're not just residents of any solar system, we're inhabitants of what may be one of the rarest, most precisely orchestrated cosmic arrangements in our entire galaxy. The story of our solar system's rarity is still unfolding, with each new exoplanet discovery adding another piece to the puzzle of just how special our cosmic neighborhood might be. But already, the evidence points to a stunning conclusion: that we live within a planetary system so unusual, so perfectly balanced, that finding another like it may be the astronomical equivalent of discovering a needle in a cosmic haystack spanning hundreds of billions of stars. Of billions of stars. Yet as we delve deeper into the cosmic census of planetary worlds, we discover that our rarity extends far beyond the simple arrangement of 8 planets around a single star. The very processes that shaped our solar system appear to have followed a path so unlikely, so dependent on precise timing and fortunate circumstances, that recreating it elsewhere seems almost impossible. Consider the mystery of what didn't form in our solar system, and how that absence makes us even more extraordinary. Among the thousands of exoplanets discovered by space telescopes, one of the most common types is something called a mini Neptune. These worlds, typically 2 to 4 times Earth's radius, appear in roughly half of all planetary systems surveyed by astronomers. They represent an intermediate size between rocky planets like Earth and ice giants like Neptune, filling what you might think of as a natural middle ground in planetary formation. Yet our solar system contains absolutely nothing like a mini Neptune. This gap in our planetary lineup is puzzling and adds another layer to our cosmic uniqueness. We have 4 small rocky worlds, then a dramatic jump to 4 massive giants with nothing in between. Theories suggest that Jupiter's early gravitational influence may have prevented such intermediate worlds from forming in our system, clearing out material that might have coalesced into these medium-sized planets. If true, this process would make our current configuration even more improbable among the galaxy's planetary families. The choreography of our formation becomes even more intricate when we examine the role of our asteroid belt, that collection of rocky debris orbiting between Mars and Jupiter. In most planetary systems, this region would likely have formed into another planet, adding to the system's roster of worlds. But in our solar system, Jupiter's gravitational influence prevented this accretion, leaving behind a scattered collection of asteroids that serves as a fossil record of our system's violent youth. This failed planet, this absence where another world might have been, represents yet another way our solar system diverges from the cosmic norm. Our uniqueness extends outward to the very edges of our solar system, where we encounter another remarkable feature that sets us apart from other known planetary arrangements. Beyond Neptune lies the Kuiper Belt, a vast region populated with icy bodies and dwarf planets like Pluto. This structure suggests that our solar system's formation process managed to preserve materials from the earliest epochs of planetary construction, creating a cosmic archaeology site that most other systems seem to lack. The precision required for maintaining this outer architecture over billions of years speaks to the remarkable stability of our gravitational environment. Most planetary systems show evidence of significant disruption in their outer regions, with planets migrating chaotically or being ejected entirely from their home systems. Our ability to maintain coherent structure from the innermost rocky worlds to the outermost icy bodies suggests a formation history remarkably free from the catastrophic events that seem to characterize most other planetary systems. But perhaps the most profound aspect of our solar system's rarity lies not in what we can easily observe, but in the subtle gravitational relationships that have maintained our stability across cosmic time. The resonances between our planets, the precise ratios of their orbital periods, create a complex symphony of gravitational influences that has prevented chaotic interactions for over 4 billion years. Jupiter and Saturn, for instance, exist in what astronomers call a near 2-to-1 resonance, with Jupiter completing nearly 2 orbits for every one that Saturn completes. These orbital relationships aren't accidents of formation, but represent the end result of a gradual settling process that occurred as our planets migrated through the debris-filled disk of our young solar system. The fact that these resonances stabilized into configurations that promote long-term stability rather than chaos represents another extraordinary aspect of our cosmic arrangement. Computer simulations suggest that most multi-planet systems either settle into unstable configurations that eventually lead to planetary collisions or ejections, or they never achieve stable resonances at all. The gravitational influence of our gas giants extends their protective effect throughout the inner solar system in ways that may be crucial for life on Earth. Jupiter and Saturn act as cosmic vacuum cleaners, their immense gravitational fields capturing or deflecting asteroids and comets that might otherwise bombard the inner planets. This protective effect, sometimes called the Jupiter shield, has likely prevented numerous extinction-level impacts on Earth throughout its history, allowing complex life to evolve and flourish over billions of years. Yet the positioning of these protective giants required extraordinary precision. Too close to the Sun, and their gravitational influence would have prevented the formation of stable rocky planets in the habitable zone. Too far away, and they couldn't provide adequate protection from incoming debris. The current positions of Jupiter and Saturn represent what appears to be an optimal configuration for protecting inner system worlds while allowing them to maintain stable, life-supporting orbits. The story of our solar system's formation also reveals another layer of improbability in the timing of various events. The late heavy bombardment, a period roughly 4 billion years ago, when the inner solar system experienced intense asteroid and comet impacts, appears to have been triggered by a reorganization of the outer planet's orbits. This event, while initially devastating, may have been crucial for delivering water and organic compounds to the early Earth, providing the raw materials necessary for life's emergence. The precise timing of this bombardment, occurring after Earth had cooled sufficiently to retain liquid water, but before life had established complex ecosystems, represents another example of the remarkable synchronization that characterizes our solar system's evolution. Too early, and the impacts would have sterilized any emerging life forms. Too late, and established ecosystems might have been destroyed beyond recovery. The window for beneficial bombardment appears to have been relatively narrow, and our solar system managed to hit that target with extraordinary precision. As we examine the broader context of planetary system formation throughout the galaxy, our solar system's path begins to look increasingly like a cosmic miracle. Current theories suggest that most planetary systems undergo periods of instability that dramatically reshape their architecture, often multiple times throughout their histories. Planets migrate inward and outward, collide with one another, or get ejected into interstellar space entirely. The violence and chaos that characterize most planetary formation processes make our solar system's relatively peaceful evolution all the more remarkable. Recent discoveries have revealed that even systems initially thought to resemble our own often harbor hidden instabilities or unusual characteristics that set them apart from our cosmic neighborhood. The Kepler Space Telescope's survey of thousands of planetary systems revealed a universe filled with arrangements that would seem alien to anyone familiar. Only with our solar system's orderly progression from small inner worlds to massive outer giants. The detection challenges that astronomers face when searching for solar systems like ours add another dimension to our apparent rarity. Most exoplanet detection methods are biased toward finding large planets in close orbits around their stars, as these create the most easily detectable signals. Earth-like planets and distant gas giants like Jupiter and Saturn are extremely difficult to detect with current technology, meaning that many solar systems similar to ours might exist but remain hidden from our observations. Yet even accounting for these observational biases, the complete absence of any detected system that closely matches our solar system's architecture suggests that configurations like ours are genuinely rare rather than simply hidden. If ordered planetary systems were common, we would expect to have found at least a few examples by now, given the thousands of systems that have been studied in detail. The implications of our solar system's rarity extend far beyond mere cosmic curiosity. If systems like ours are truly as uncommon as current evidence suggests, it fundamentally changes how we think about the prevalence of Earth-like worlds and the potential for life throughout the galaxy. The specific arrangement of planets in our system may not just be unusual, but may actually be necessary for the long-term stability and habitability that allowed complex life to evolve on our pale blue dot. Blue dot. Our solar system's exceptional nature becomes even more apparent when we consider the remarkable characteristics of Earth's relationship with its unusually large moon. Among terrestrial planets throughout the galaxy, Earth's lunar companion stands out as an anomaly of extraordinary proportions. Most rocky worlds either possess no moons at all or harbor tiny satellites that exert minimal gravitational influence on their host planets. Our moon, however, represents something entirely different. A companion so substantial relative to Earth's size that some astronomers consider our world to be part of a double planet system, rather than a traditional planet-moon arrangement. The formation of such an oversized lunar companion required an event so catastrophic and precisely orchestrated that recreating it seems almost impossible. Current theories suggest that our moon emerged from the debris of a Mars-sized object that collided with the early Earth at just the right angle, with just the right velocity, and at just the right moment in our planet's formation. This cosmic collision, known as the giant impact hypothesis, had to occur after Earth had differentiated into core and mantle, but before the planet had cooled too much to allow the debris to coalesce into our current moon. The timing window for this impact was remarkably narrow. Too early in Earth's formation, and the collision would have disrupted the planet's basic structure. Too late, and the debris would have been too cold and dispersed to form a substantial satellite. The impactor had to be large enough to create sufficient debris for moon formation, but not so large as to completely destroy the proto-Earth. The collision angle had to be oblique rather than head-on, allowing material to be ejected into orbit rather than simply blasting it away into space. This lunar companion has profoundly influenced Earth's habitability in ways that most planets throughout the galaxy never experience. Our moon's gravitational pull creates ocean tides that have played a crucial role in Earth's dynamic climate system. These tidal forces ensure that our oceans remain in constant motion rather than stagnating, promoting the circulation patterns that distribute heat around our planet and maintain the chemical cycles necessary for life. The churning action of tides may have even helped facilitate the transition of life from ocean to land by creating intertidal zones where organisms could gradually adapt to terrestrial conditions. Perhaps even more importantly, our moon serves as a celestial stabilizer, moderating Earth's axial tilt and preventing the chaotic wobbling that would otherwise result from gravitational perturbations by other planets. Without this lunar stabilization, Earth's axis could vary dramatically over relatively short geological timescales, causing extreme climate variations that would make the long-term evolution of complex life nearly impossible. Mars, lacking a substantial moon, experiences axial tilt variations from 13 to 40 degrees over periods of just 5 to 10 million years, creating climate instabilities that will be devastating for any complex ecosystems. The protective influence of our moon extends beyond tidal and axial stabilization. Its gravitational presence has helped shape the asteroid belt structure and may have influenced the timing and intensity of impact events throughout Earth's history. Some researchers suggest that without our moon's gravitational influence, Earth might have experienced either too many catastrophic impacts, preventing life from gaining a foothold, or too few impacts, failing to deliver the water and organic compounds necessary for life's emergence. Yet the moon's beneficial effects required not just its formation, but its current orbital characteristics. Our lunar companion orbits at precisely the right distance to provide optimal tidal effects without being so close as to create destructive tidal forces that would tear apart Earth's crust. It's massive enough to stabilize our planet's rotation, but not so massive as to tidally lock Earth, which would create extreme temperature differences between our planet's day and night sides. The moon's nearly circular orbit ensures consistent tidal patterns rather than the chaotic variations that would result from a highly elliptical path. The probability of achieving all these precise characteristics through natural processes appears vanishingly small. Among the thousands of exoplanets discovered so far, astronomers have found no clear examples of Earth-sized worlds with moon-sized companions. let alone companions that provide similar stabilizing effects. This absence could partly reflect the difficulty of detecting moons around distant planets, but it also suggests that the giant impact scenario that created our moon may be an extraordinarily rare occurrence in planetary formation. Beyond our moon's influence, Earth's position within our solar system represents another layer of cosmic fine-tuning that sets us apart from other worlds. We orbit within what astronomers call the habitable zone, that narrow band of space around our star where liquid water can exist on a planet's surface. But simply being in this zone isn't sufficient for habitability. Earth's orbit is remarkably stable and nearly circular, maintaining relatively consistent temperatures year-round and avoiding the extreme seasonal variations that would result from a highly elliptical path. This orbital stability exists partly because of the gravitational architecture of our entire solar system. The spacing between planets, their relative masses, and their orbital resonances all contribute to maintaining Earth's stable path around the Sun. Jupiter's massive presence particularly influences Earth's orbit, preventing it from becoming more elliptical due to gravitational perturbations from other planets. Without Jupiter's stabilizing influence, Earth's orbit might vary enough to push our planet outside the habitable zone periodically, creating ice ages so severe that complex life could never establish itself. The chemical composition of Earth itself reflects another aspect of our solar system's unusual formation history. Our planet contains just the right mixture of elements to support the complex chemistry of life while maintaining the geological processes that regulate our climate over long timescales. This chemical balance resulted from the specific conditions present in our region of the protoplanetary disk when Earth formed, conditions that appear to have been influenced by the unusual metallicity of our Sun and the precise timing of various formation events. Earth's magnetic field provides yet another example of the extraordinary circumstances that make our world habitable. Generated by the motion of molten iron in our planet's outer core, this magnetic field deflects harmful solar wind particles and cosmic radiation that would otherwise strip away our atmosphere and sterilize our surface. The strength and stability of Earth's magnetic field depend on our planet's size, composition, rotation rate, and internal structure, all of which had to align properly during our world's formation. Many planets throughout the galaxy either never develop substantial magnetic fields or lose them early in their histories as their cores cool and solidify. Mars, for instance, appears to have lost its magnetic field billions of years ago, allowing its atmosphere to be gradually stripped away by solar wind. Venus, despite being similar in size to Earth, lacks a significant magnetic field, possibly due to its extremely slow rotation. The precise combination of factors that maintain Earth's protective magnetic field over billions of years appears to be another rare characteristic of our cosmic neighborhood. The story of our solar system's rarity extends even to the broader galactic environment in which we formed. Our Sun's current position within the Milky Way places us in what some astronomers call the Galactic Habitable Zone, a region far enough from the galaxy's center to avoid disruptive radiation and gravitational effects from the supermassive black hole that anchors our galaxy, yet not so far out that heavy elements necessary for planet formation are scarce. But our galactic position hasn't remained constant throughout our solar system's history. Like all stars, our Sun orbits around the galaxy's center, completing one revolution approximately every 250 million years. During this galactic year, our solar system passes through various regions of the galaxy, some more hospitable to life than others. We currently reside between major spiral arms, in a relatively quiet region with lower rates of star formation and supernova explosions that might otherwise disrupt planetary atmospheres with deadly radiation. The timing of our solar system's formation within the galaxy's chemical evolution also appears to have been fortuitous. We formed at a time when the galaxy had produced sufficient quantities of heavy elements through previous generations of stellar nucleosynthesis, providing the raw materials necessary for rocky planet formation, yet not so late that our stellar neighborhood had become overly crowded or metal-rich. This chemical timing, combined with our current galactic position, represents another layer of circumstance that contributes to our cosmic rarity. As we continue to discover more about exoplanetary systems throughout the galaxy, each new finding seems to reinforce rather than diminish our solar system's exceptional nature. The absence of any detected system that closely matches our arrangement, combined with the growing understanding of the precise conditions required for long-term planetary stability, paints a picture of cosmic circumstances so unlikely that they challenge our understanding of planetary formation itself. Recent studies of stellar nurseries where new planets are currently forming reveal chaotic environments filled with gravitational interactions, collisions, and migrations that rarely result in the ordered, stable arrangements we observe in our own cosmic neighborhood. The violence and unpredictability that characterize most planetary formation processes make our solar system's relatively peaceful evolution appear increasingly miraculous with each new observation. Yet perhaps the most profound aspect of our rarity lies not in any single characteristic, but in the extraordinary convergence of all these factors within a single system. The precise stellar type, the unusual metallicity, the ordered planetary architecture, the protective gas giants, the stabilizing moon, the galactic position, the formation timing, each element by itself might be uncommon, but not impossible. But their simultaneous occurrence within one system creates a confluence of circumstances so improbable that it transforms our cosmic address from merely unusual to genuinely extraordinary. Unusual to genuinely extraordinary. The deeper we venture into our solar system's cosmic biography, the more we encounter formations and relationships so precisely calibrated that they seem to whisper of some hidden cosmic artistry at work. Consider the delicate gravitational resonances that have maintained harmony among our worlds for over 4 billion years, preventing the chaotic collisions and ejections that characterize most other planetary families we've observed. These aren't mere coincidences of celestial mechanics, but represent the end result of a formation process so finely tuned that recreating it elsewhere appears nearly impossible. Jupiter and Saturn dance in what astronomers call a near 2-to-1 resonance, with Jupiter completing almost exactly 2 orbits for every single orbit that Saturn traces around our Sun. This mathematical relationship isn't arbitrary, but emerged from millions of years of gradual orbital adjustment as these giant worlds settled into their current positions. The precision required for achieving such stable resonances staggers the imagination. Computer simulations reveal that most multi-planet systems either fail to achieve any resonant relationships at all, leading to eventual orbital chaos, or they settle into unstable configurations that ultimately result in planetary collisions or ejections into the cold depths of interstellar space. Our solar system, somehow managed to thread the needle, achieving a gravitational balance so exquisite that it has persevered across geological epochs. But the story becomes even more remarkable when we examine what astronomers call the Late Heavy Bombardment, a period roughly 4 billion years ago when our inner solar system experienced an intense shower of asteroids and comets. This cosmic catastrophe, while initially appearing destructive, may have been perfectly timed to deliver the water and organic compounds that made life on Earth possible. The bombardment occurred after our planet had cooled sufficiently to retain liquid oceans, but before complex ecosystems had established themselves. The timing window for this beneficial bombardment appears to have been extraordinarily narrow. Too early, and the impacts would have vaporized any water that had begun to accumulate on Earth's surface. Too late, and any emerging life forms would have been sterilized by the cosmic violence. Yet our solar system managed to orchestrate this delivery of life's essential ingredients with a precision that seems almost purposeful in its accuracy. This bombardment event itself resulted from a reorganization of our outer planet's orbits, triggered by gravitational interactions between Jupiter, Saturn, and the smaller ice giants beyond them. The fact that this orbital reshuffling occurred at precisely the right moment in Earth's development represents another layer of improbable timing that characterizes our cosmic neighborhood's evolution. As we peer outward toward the edge of our solar system, we encounter yet another testament to our extraordinary nature. The Kuiper Belt, that vast collection of icy bodies beyond Neptune's orbit, preserves materials from the earliest epochs of our system's formation, like a cosmic time capsule. This structure suggests that our formation process managed to maintain coherent organization from the innermost rocky worlds to the outermost frozen remnants of the primordial disk from which we emerged. Most other planetary systems show evidence of significant disruption in their outer regions, with materials scattered chaotically or ejected entirely from their home systems during periods of instability. Our ability to maintain structured architecture across such vast distances speaks to a formation history remarkably free from the catastrophic events that seem to define most other cosmic neighborhoods. The protective influence of our gas giants extends far beyond their gravitational stabilization of inner planet orbits. Jupiter and Saturn act as cosmic guardians, their immense gravitational fields capturing or deflecting dangerous asteroids and comets that might otherwise rain destruction upon the terrestrial worlds where life can flourish. This protective effect, sometimes called the Jupiter shield, has likely prevented countless extinction-level impacts on Earth throughout its 4.5 billion-year history. Yet achieving this protective configuration required extraordinary precision in planetary positioning. Too close to the Sun, and Jupiter's gravitational influence would have prevented the formation of stable rocky planets in the habitable zone where liquid water can exist. Too distant, and it couldn't provide adequate protection from incoming debris. The current arrangement represents what appears to be an optimal balance between protection and planetary formation, a cosmic sweet spot that few other systems seem to achieve. The chemical fingerprint of our solar system tells another story of improbable circumstances. Our Sun's unusual abundance of heavy elements, that metallicity anomaly known as the G-dwarf problem, provided the raw materials necessary for forming rocky planets like Earth. This metal-rich composition suggests our star may have migrated from a different region of the galaxy where such conditions were more common, carrying its enhanced chemistry to our current galactic location, where it could nurture a family of diverse worlds. But even this chemical abundance had to occur at precisely the right moment in our galaxy's evolution. Too early and insufficient heavy elements would have existed to form terrestrial planets. Too late, and our stellar neighborhood might have become overcrowded or chemically polluted in ways that would have disrupted planetary formation. The timing of our Sun's birth within the galaxy's chemical evolution appears to have been exquisitely calibrated to provide optimal conditions for creating the diverse planetary family we observe today. The absence of certain types of worlds in our solar system adds another dimension to our cosmic uniqueness. Mini-Neptunes, those intermediate-sized worlds between Earth and Neptune that populate roughly half of all known planetary systems, are completely absent from our cosmic neighborhood. This gap in our planetary roster isn't merely unusual, but represents a fundamental difference in formation history that sets us apart from the galactic norm. Theories suggest that Jupiter's early gravitational influence prevented such intermediate worlds from accumulating in our system, clearing away material that might have coalesced into these medium-sized planets. If accurate, this process would make our current configuration even more improbable, requiring not just the right conditions for forming what we see, but also the right conditions for preventing what we don't observe. The broader galactic context in which our solar system exists adds yet another layer to our cosmic rarity. Our Sun's solitary nature stands out in a universe where most stars exist in binary or multiple star systems. These complex gravitational environments create challenging conditions for stable planetary formation, often resulting in worlds with highly elliptical orbits or planets being ejected entirely from their systems during close encounters with stellar companions. Our stellar isolation has allowed for the formation of those remarkably circular planetary orbits that have remained undisturbed for billions of years. In a galaxy where cosmic loneliness is the exception rather than the rule, our Sun's single status becomes another mark of distinction that contributes to our system's overall habitability and long-term stability. Even our position within the galaxy itself appears to be fortuitously chosen. We reside in what some astronomers call the Galactic Habitable Zone, far enough from the galaxy's turbulent center to avoid disruptive radiation and gravitational effects, yet not so distant that heavy elements necessary for rocky planet formation become scarce. This cosmic real estate represents prime galactic territory for supporting the long-term evolution of complex planetary systems. But our galactic address hasn't remained constant throughout our solar system's lifetime. Like all stars, our Sun orbits the galactic center, completing one revolution every 250 million years or so. During these galactic seasons, we pass through various regions with different characteristics and hazards. Currently, we find ourselves between major spiral arms, in a relatively quiet neighborhood with lower rates of violent star formation and supernova explosions that might otherwise sterilize planetary atmospheres with deadly radiation. The timing of our current galactic position coincides remarkably with the emergence and evolution of complex life on Earth. Had we been passing through a more active region of the galaxy during the critical periods when life was establishing itself on our planet, the additional radiation and gravitational disturbances might have prevented or reversed the evolutionary processes that led to the rich biosphere we observe today. as astronomical surveys continue to catalogue thousands of exoplanetary systems throughout our galaxy. The complete absence of any arrangement that closely matches our solar system's architecture becomes increasingly significant. Even accounting for the observational biases that make Earth-like worlds and distant gas giants difficult to detect, the lack of any discovered system resembling our cosmic neighborhood suggests that configurations like ours represent genuine rarity rather than hidden abundance. Recent studies of young stellar systems where planets are currently forming reveal chaotic environments filled with gravitational violence, orbital migrations, and planetary collisions that rarely result in the ordered stability we observe around our middle-aged sun. The peaceful evolution that characterizes our solar system's formation appears to be the exception rather than the rule in the galaxy's ongoing planetary construction projects. Each new discovery in exoplanetary science seems to reinforce rather than diminish our cosmic exceptionalism. Hot Jupiters spiraling close to their stars, super-Earths with no analogue in our system, chaotic arrangements of worlds in highly elliptical orbits, all paint a picture of a galaxy filled with planetary architectures that would seem alien to anyone familiar only with our orderly progression from small inner worlds to massive outer giants. The implications of our solar system's rarity extend far beyond astronomical curiosity. If systems like ours are truly as uncommon as mounting evidence suggests, it fundamentally transforms our understanding of how frequently Earth-like conditions might arise throughout the galaxy. The specific arrangement of worlds in our system may not simply be unusual, but may actually be necessary for the long-term stability that allowed complex chemistry to evolve into the magnificent complexity we call life. As you drift deeper into contemplation of these cosmic truths, consider that every breath you take, every heartbeat that sustains you, every thought that flows through your consciousness unfolds within this extraordinarily rare cosmic arrangement. You are not merely an observer of this galactic rarity, but an integral part of it. A temporary flowering of complexity that has emerged from the precise gravitational choreography of worlds that took billions of years to achieve their current sublime configuration. The profound rarity of our cosmic home reveals itself not just in grand architectural arrangements, but in countless subtle details that most planetary systems seem unable to achieve. Consider the exquisite balance of forces that governs our asteroid belt, that scattered collection of rocky debris orbiting between Mars and Jupiter. In most other systems, this region would likely have coalesced into another planet, adding one more world to the celestial census. But Jupiter's gravitational presence prevented this accumulation, leaving behind a fossil record of our system's early violence while simultaneously creating a protective barrier that helps shield the inner planets from dangerous impacts. This failed planet, this cosmic absence where another world might have formed, represents yet another way our solar system diverges from galactic norms. The precise gravitational balance required to maintain this asteroid belt's current structure over billions of years speaks to a level of stability that most planetary systems never achieve. Too little gravitational influence, and the asteroids would have scattered throughout the solar system, creating a hazardous environment for terrestrial worlds. Too much influence, and they would have been swept up entirely, eliminating their protective function. The story becomes even more intricate when we examine the role of our ice giants, Uranus and Neptune, in sculpting the outer reaches of our cosmic neighborhood. These distant worlds, with their unusual tilts and complex magnetic fields, appear to have migrated outward during the early epochs of our system's formation, clearing debris from their paths while establishing the boundaries of our current architecture. Their journey outward triggered cascading effects throughout the system, influencing everything from the timing of the late heavy bombardment to the current structure of the Kuiper belt. Most remarkably, this migration occurred without destabilizing the inner planets or disrupting the delicate gravitational relationships that maintain our system's long-term stability. Computer simulations reveal that such migrations typically result in chaotic interactions that either eject planets entirely or send them careening into their parent stars. Our ice giants somehow manage to relocate themselves while preserving the harmony of the entire system, an achievement that appears almost impossibly unlikely when viewed against the backdrop of typical planetary evolution. The thermal environment of our solar system adds another layer of improbable precision to our cosmic arrangement. Each planet maintains temperatures that reflect not just its distance from the Sun, but also its atmospheric composition, geological activity, and the complex interplay of greenhouse effects and reflective surfaces. Earth's temperature regulation system, with its intricate cycles of water evaporation, cloud formation, and precipitation, creates a self-stabilizing mechanism that has maintained liquid oceans for nearly 4 billion years, despite significant changes in solar luminosity over that same period. This climatic stability required not just the right initial conditions, but also the ongoing geological processes that regulate atmospheric composition over vast timescales. Plate tectonics, that slow dance of crustal movement that characterizes our planet's surface, plays a crucial role in cycling carbon between the atmosphere and the solid Earth. This geological thermostat helps maintain temperatures within the narrow range where liquid water can exist, preventing our world from becoming either a frozen ice ball or a scorching greenhouse like Venus. The magnetic environment of our solar system tells another story of extraordinary coordination between multiple worlds. Earth's protective magnetic field, generated by the motion of molten iron in our planet's core, deflects harmful solar wind particles that would otherwise strip away our atmosphere. But this magnetic protection exists within a larger magnetic architecture that includes the Sun's own magnetic field and the magnetic environments of our gas giant planets. Jupiter's immense magnetosphere, stretching millions of kilometers into space, acts as an additional shield that helps protect the inner solar system from galactic cosmic rays and charged particles from deep space. This layered magnetic protection system required the precise coordination of planetary sizes, compositions, rotation rates, and internal structures across multiple worlds, creating a nested series of protective barriers that few other systems appear to achieve. The chemical evolution of our solar system reveals yet another dimension of its extraordinary nature. The gradual enrichment of heavy elements through stellar nuclear synthesis had to occur at precisely the right rate to provide the building blocks for rocky planet formation, without creating conditions so metal-rich that gas giant formation would be suppressed. Our Sun's enhanced metallicity, that puzzling abundance of heavy elements for a star of its age and galactic location, appears to have been crucial for creating the chemical diversity we observe among our planets. But this chemical abundance had to be distributed throughout the protoplanetary disk in just the right proportions. Too much concentration of heavy elements in the inner regions and super-Earths might have formed instead of the smaller terrestrial worlds we observe. Too little concentration, and rocky planets might not have formed at all. The chemical gradient that existed in our early solar nebula appears to have been calibrated with extraordinary precision to produce the specific types of worlds we see today. The temporal choreography of our formation adds another layer of improbable coordination to our cosmic story. The sequence of events that led to our current configuration had to unfold in precisely the right order, with each major milestone occurring at exactly the right moment to enable the next phase of development. The formation of Jupiter had to occur early enough to prevent super-Earths from forming in the inner system, but late enough to allow sufficient material to remain for terrestrial planet construction. The timing of planetary migration, the onset of the late heavy bombardment, the stabilization of orbital resonances, the delivery of water to Earth. Each of these critical events required not just the right conditions, but also the right sequence. A different timing for any of these processes could have resulted in a completely different planetary arrangement, one potentially hostile to the emergence and evolution of complex life. The preservation of our system's early history in various reservoirs throughout our cosmic neighborhood provides evidence of formation processes that most other systems seem unable to maintain. The Kuiper Belt preserves icy materials from the outer regions of our primordial disk, while meteorites carry samples of the rocky components that formed closer to the Sun. This cosmic archaeology reveals a formation process that managed to create and maintain distinct populations of materials across vast distances and timescales. Most other planetary systems show evidence of significant mixing and disruption that would have homogenized these materials, erasing the chemical signatures that tell us about different formation environments. Our ability to read the detailed history of our system's birth in these preserved samples speaks to a remarkably gentle and organized formation process that avoided the violent disruptions characteristic of most other cosmic neighborhoods. The resonant relationships between our moons add yet another layer of complexity to our system's gravitational architecture. The four largest moons of Jupiter dance in precise mathematical relationships with one another, their orbital periods locked in ratios that maintain long-term stability despite the complex gravitational environment of the Jovian system. Saturn's moon system displays similar resonant structures, creating stable configurations that have persisted for billions of years. These satellite systems represent miniature versions of the same organizational principles that govern our planetary arrangement, suggesting that the processes that created our solar system's architecture operated consistently across different scales and environments. The ability to create and maintain such complex resonant structures simultaneously in multiple locations throughout our system speaks to an underlying organizational principle that few other cosmic neighborhoods seem to achieve. The optical environment of our solar system, the way light propagates and interacts throughout our cosmic neighborhood, reveals another aspect of our exceptional nature. The clarity of space between our planets allows for precise astronomical observations that have enabled our understanding of cosmic distances and the expansion of the universe itself. Many other planetary systems exist in environments cluttered with debris or dust that would obscure such observations, potentially limiting the astronomical knowledge that could develop in those systems. Our relatively clean interplanetary medium results from the efficient clearing of debris during our formation process. and the ongoing gravitational shepherding by our gas giants. This cosmic housekeeping has created an environment where light can travel unimpeded across vast distances, enabling not just scientific observations, but also the stable energy delivery from our Sun that powers the complex chemistry of life on Earth. The electromagnetic environment of our solar system displays a complexity and organization that appears to be rare among known planetary arrangements. The interaction between the solar wind, planetary magnetic fields, and various populations of charged particles creates a dynamic system of electromagnetic phenomena that has remained stable for billions of years. This electromagnetic architecture influences everything from atmospheric retention on rocky planets to the formation of auroras that dance in our polar skies. The precise calibration of these electromagnetic interactions required the coordination of multiple factors across our entire system. Solar wind strength, planetary magnetic field configurations, atmospheric compositions, and the distribution of charged particles all had to align to create the current stable electromagnetic environment. Most other systems appear to lack this level of electromagnetic organization, suggesting that achieving such coordination represents another improbable aspect of our cosmic arrangement. As we continue to catalogue the myriad ways our solar system differs from other known planetary arrangements, each new layer of complexity reveals the extraordinary improbability of our cosmic circumstances. We exist within a system so precisely orchestrated, so dependent on the coordination of countless variables, that reproducing it elsewhere seems to require not just favorable conditions, but an almost miraculous convergence of circumstances across vast scales of space and time. The mounting evidence for our solar system's rarity doesn't diminish our cosmic significance, but rather amplifies it, suggesting that we may be inhabitants of one of the galaxy's most extraordinary achievements in planetary organization. Every sunset you witness, every gentle breeze that carries the scent of growing things, every moment of wonder as you contemplate the night sky, all unfold within this remarkable cosmic arrangement that may be far more precious and unique than we ever dared imagine. The detection challenges that face astronomers searching for systems like ours reveal yet another dimension of our cosmic rarity. Most exoplanet discovery methods suffer from inherent biases that favor finding large planets orbiting close to their stars, as these create the strongest and most easily detectable signals. The radial velocity technique picks up the gravitational wobble that massive planets induce in their host stars. But this wobble becomes increasingly subtle as planets move farther away and take longer to complete their orbits. Transit photometry, which detects the slight dimming when a planet passes in front of its star, requires extraordinary patience and precision to catch distant worlds. Jupiter takes 12 years to complete one orbit around our Sun, meaning that detecting a Jupiter-like planet would require observing its star system for at least that long to catch even a single transit event. Saturn, with its nearly 30-year orbital period, would demand observations spanning multiple decades to confirm its presence through repeated transits. These observational limitations mean that if there were an alien civilization orbiting a star 12 light-years away, equipped with technology identical to our most advanced instruments, they would struggle to detect our complete planetary family. They might catch Venus crossing the Sun's disk relatively frequently, perhaps notice Earth's annual transit, and after years of careful observation, they might detect Jupiter's gravitational influence on our star. But Saturn, Uranus, and Neptune would likely remain hidden, leading these hypothetical astronomers to conclude that our solar system contains perhaps 2 to 4 planets, rather than the 8 we actually harbor. This detection bias has profound implications for our understanding of how common solar systems like ours might actually be throughout the galaxy. The absence of detected systems matching our architecture could reflect not genuine rarity, but rather the fundamental limitations of our current observational capabilities. Yet even accounting for these biases, the complete lack of any discovered system closely resembling our ordered planetary arrangement suggests that configurations like ours represent authentic cosmic scarcity rather than hidden abundance. Recent advances in gravitational wave astronomy have opened new windows into the violent processes that shape most planetary systems throughout their evolution. The detection of merging black holes and neutron stars reveals a universe filled with catastrophic events that would sterilize any nearby planetary systems, stripping away atmospheres and disrupting the delicate orbital mechanics necessary for long-term stability. Our solar system's location in a relatively quiet region of the galaxy, far from such destructive phenomena, represents another layer of fortunate circumstance that contributes to our cosmic exceptionalism. The chemical signatures preserved in meteorites that occasionally fall to Earth carry messages from the earliest epochs of our solar system's formation, revealing formation processes that appear to have been remarkably organized compared to the chaotic environments observed in young stellar systems today. These ancient rocks preserve evidence of precise temperature gradients, controlled chemical mixing, and gentle accretion processes that stand in stark contrast to the violent collisions and disruptions that characterize most planetary formation scenarios. The isotopic ratios found in these primordial samples tell stories of stellar nucleosynthesis events that occurred in previous generations of stars, whose deaths enriched the cosmic medium with the heavy elements necessary for rocky planet formation. But the specific mixture of isotopes preserved in our meteorites suggests that our solar system formed from material contributed by multiple stellar sources, each adding its own chemical signature to the cosmic recipe that would eventually become our planetary family. This multi-source heritage required extraordinary timing, with various stellar deaths occurring at precisely the right moments to enrich our local galactic environment with the optimal mixture of elements. Too much contribution from certain types of stellar explosions, and our forming solar system would have been contaminated with unstable isotopes that would have made long-term planetary development impossible. Too little contribution from others, and we would have lacked the heavy elements necessary for terrestrial world formation. The preservation of these chemical signatures over billions of years speaks to formation conditions so gentle and well organized that they avoided the violent mixing and homogenization that characterizes most other planetary construction projects. Our solar system somehow managed to maintain distinct chemical populations from different formation environments, while simultaneously creating the gravitational architecture that governs our current orbital relationships. The role of our solar system's location within the galactic disk adds another temporal dimension to our cosmic story. Star formation rates, supernova frequencies, and the abundance of heavy elements all vary significantly depending on position within the galaxy and time since the galaxy's formation. Our Sun appears to have formed at precisely the right moment in galactic chemical evolution, when enough heavy elements had accumulated to enable terrestrial planet formation, But before our stellar neighborhood became overcrowded or chemically polluted, the galactic orbital mechanics that govern our sun's motion around the galaxy's center create a complex pattern of encounters with different galactic environments over cosmic time. Spiral arm passages, interactions with molecular clouds, and variations in the local stellar density all influence the conditions experienced by our solar system throughout its lifetime. The fact that these galactic seasons have coincided favorably with the critical periods of planetary development and biological evolution on Earth represents another layer of improbable timing. Current observations of star-forming regions throughout the galaxy reveal environments so chaotic and violent that the gentle, organized formation process our solar system appears to have experienced seems almost miraculous by comparison. Young stellar clusters teem with gravitational interactions, close encounters between forming planetary systems, and radiation fields so intense they can photo-evaporate entire protoplanetary disks before planets have a chance to form. Our solar system somehow avoided these destructive influences during its vulnerable early phases, forming in an environment calm enough to allow the delicate processes of planetary accretion to proceed undisturbed. This environmental serenity during our formation epoch required not just favorable local conditions, but also fortunate timing that avoided the periods of intense star formation activity that characterize most galactic regions. The magnetic field structure of our solar system reveals another aspect of extraordinary organization that few other planetary arrangements appear to achieve. The complex interplay between the Sun's magnetic field, the solar wind it generates, and the magnetic environments of our individual planets creates a nested hierarchy of protective barriers that shields our inner worlds from harmful cosmic radiation while maintaining the stable space weather conditions necessary for atmospheric retention. This magnetic architecture required the precise coordination of stellar rotation rates, planetary core compositions, and the electromagnetic properties of the interplanetary medium. Most other stellar systems appear to lack this level of magnetic organization, either because their host stars rotate too quickly or too slowly to generate appropriate magnetic fields, or because their planetary configurations create unstable electromagnetic environments. The acoustic properties of our solar system, the way sound waves and other pressure disturbances propagate through the various gaseous environments of our planets, reveal yet another dimension of our cosmic uniqueness. The specific atmospheric compositions and pressure profiles of our gas giants create resonant cavities that have influenced the long-term evolution of these worlds' internal structures and atmospheric dynamics. These acoustic environments arose from the precise balance of formation conditions that determined each planet's final composition and internal architecture. Too much or too little of various atmospheric components, and these resonant structures would never have developed, potentially leading to unstable atmospheric evolution that could have disrupted the gravitational relationships maintaining our system's overall stability. The optical properties of our solar system's various components create viewing conditions that have enabled the astronomical observations leading to our understanding of cosmic distances, stellar evolution, and the expanding universe itself. The transparency of our interplanetary medium, the reflective properties of our planets and moons, and the unobstructed sightlines to distant cosmic phenomena have all contributed to the development of the astronomical knowledge that reveals our place in the cosmic order. Many other planetary systems exist in environments cluttered with debris, dust, or other optical obstacles that would severely limit the astronomical observations possible from worlds within those systems. The clarity of our cosmic neighborhood results from the efficient debris clearing that occurred during our formation and the ongoing gravitational maintenance provided by our gas giants, creating conditions conducive not just to planetary stability, but also to the development of astronomical understanding. The hydrodynamic environment of our solar system, governed by the flow patterns of the solar wind and the atmospheric circulation of our various worlds, displays a complexity and stability that appears to be rare among known planetary arrangements. The interaction between charged particle flows, magnetic field structures, and gravitational influences creates a dynamic system that has maintained remarkable consistency over billions of years, while remaining responsive to the subtle changes that accompany stellar evolution. This hydrodynamic stability required the coordination of countless variables across our entire system, from the Sun's rotation rate and magnetic field strength to the atmospheric compositions and magnetic properties of individual planets. The precise calibration necessary to maintain stable flow patterns while avoiding the chaotic instabilities that plague most other systems represents another improbable achievement of our cosmic architecture. The seismic environment of our terrestrial worlds reveals formation processes so gentle and well organized that they preserve the internal structures necessary for long-term geological activity. Plate tectonics on Earth, the subtle gravitational flexing that maintains geological activity on some of our moons, and the internal differentiation that powers magnetic field generation, all depend on internal structures that could only have formed under very specific conditions. Most rocky planets throughout the galaxy appear to have experienced formation processes so violent that they disrupted the internal organization necessary for sustained geological activity. The preservation of these internal structures throughout our system's terrestrial worlds speaks to formation conditions remarkably free from the catastrophic impacts and gravitational disruptions that characterize most other planetary construction projects. As we approach the completion of our cosmic census, tallying the myriad ways our solar system differs from other known planetary arrangements, the picture that emerges is one of extraordinary improbability, cascading across multiple scales of space and time. We inhabit a system so precisely orchestrated, so dependent on the coordination of countless variables, that reproducing it elsewhere appears to require not merely favorable conditions, but an almost miraculous convergence of circumstances spanning the formation and evolution of our entire galactic neighborhood. Every aspect of our cosmic home, from the chemical composition of our sun to the orbital resonances of distant moons, from the timing of planetary migration to the preservation of primordial materials, tells the same story of improbable precision and extraordinary rarity. We are not merely residents of any solar system, but inhabitants of what may be one of the galaxy's most remarkable achievements in cosmic architecture, a planetary arrangement so special that finding another like it may prove to be the astronomical equivalent of discovering the rarest of cosmic treasures hidden among hundreds of billions of stellar families scattered throughout our galaxy. The profound implications of this rarity extend far beyond astronomical curiosity, fundamentally reshaping our understanding of our place in the cosmic story and the precious nature of the world we call home. As you continue your journey through this gentle evening contemplation, remember that every moment of your existence unfolds within this extraordinarily rare cosmic masterpiece, making you not just an observer of astronomical wonder, but an integral part of one of the universe's most improbable and beautiful creations. But the story of our solar system's rarity reaches even deeper into the fundamental physics that governs cosmic evolution, revealing layers of improbability that stretch back to the very moment when matter first began organizing itself into the structures we observe today. The quantum mechanical processes that determined how our protoplanetary disk would fragment and collapse operated within probability spaces so vast that achieving our current configuration required navigating through an almost infinitely narrow pathway of successful outcomes. Consider the delicate balance of forces that had to align during the earliest moments of our system's condensation from the primordial nebula. The rate of gravitational collapse had to proceed at precisely the right pace, neither so slowly that our forming disk would be disrupted by external influences, nor so rapidly that it would fragment chaotically into an unstable collection of competing gravitational centers. This collapse rate depended on countless variables, from the initial density fluctuations in our local region of space to the subtle magnetic field structures that threaded through the interstellar medium. The thermal evolution of our forming system required equally precise calibration. As gravitational potential energy converted to heat during the collapse process, our protosolar disk had to maintain temperature gradients that would allow different types of materials to condense at appropriate distances from the forming sun. Too much heat retention, and rocky materials couldn't solidify in the inner regions where terrestrial planets needed to form. Too rapid cooling, and the chemical differentiation processes that created distinct planetary compositions would never have occurred. The magnetic field environment during our formation epoch played a crucial role in determining how angular momentum would be distributed throughout our developing system. The interaction between the young sun's magnetic field and the surrounding disk material created what astronomers call magneto-rotational instabilities, processes that helped transport angular momentum outward while allowing material to spiral inward toward our forming star. This magnetic choreography had to operate with extraordinary precision to create the current distribution of planetary masses and orbital characteristics we observe today. Most young stellar systems appear to experience magnetic field evolution that either prevents efficient planet formation entirely or creates unstable configurations that lead to subsequent disruption. Our system somehow achieved the optimal magnetic field strength and geometry to facilitate planetary construction while maintaining the long-term stability necessary for billions of years of subsequent evolution. This magnetic fine-tuning represents another thread in the complex tapestry of circumstances that makes our cosmic neighborhood so extraordinary. The nucleosynthetic heritage preserved in our planetary materials tells stories of stellar death and rebirth spanning millions of years before our own system's formation. The specific isotopic signatures found in meteorites and planetary samples reveal contributions from multiple types of stellar explosions, each occurring at precisely the right time and distance to enrich our local galactic environment with optimal proportions of heavy elements. Too much contribution from certain types of supernovae, and our forming planets would have been contaminated with short-lived radioactive isotopes that would have made long-term stability impossible. The preservation of these ancient nucleosynthetic signatures required formation processes so gentle that they avoided the violent mixing and reprocessing that characterizes most other planetary construction projects. Our solar system managed to maintain chemical memory of its stellar ancestry, while simultaneously creating the gravitational architecture that governs our current relationships, suggesting formation conditions of remarkable tranquility compared to the chaotic environments observed in most star-forming regions. The rotational properties of our planetary family reveal another dimension of extraordinary coordination that few other systems appear to achieve. The distribution of angular momentum among our worlds, from Mercury's slow rotation to Jupiter's rapid spin, reflects formation processes that manage to create stable rotational states across vastly different planetary masses and compositions. Most other planetary systems show evidence of chaotic rotational evolution, with planets either tidally locked to their stars or spinning so rapidly that they become unstable. Our system's rotational architecture required not just appropriate initial conditions, but also the long-term gravitational interactions that have maintained rotational stability over billions of years. The tidal forces exerted by planetary companions, the gravitational torques from orbital resonances, and the subtle effects of solar radiation pressure all had to combine in ways that preserved rather than disrupted the rotational characteristics necessary for planetary habitability. The atmospheric evolution pathways followed by our terrestrial worlds demonstrate another aspect of our system's remarkable precision. Each rocky planet developed atmospheric characteristics perfectly suited to its distance from the Sun and its gravitational environment, creating a diverse collection of atmospheric laboratories that spans the full range from Venus's crushing greenhouse to Mars's tenuous envelope. This atmospheric diversity arose from formation processes that delivered appropriate volatile inventories to each world, while maintaining the orbital stability necessary for long-term atmospheric evolution. Most other terrestrial planets throughout the galaxy appear to have experienced atmospheric evolution so chaotic that they either lost their atmospheres entirely or developed atmospheric compositions hostile to any form of complex chemistry. Our system's ability to nurture and maintain diverse atmospheric environments across multiple worlds speaks to formation and evolution processes of extraordinary sophistication and stability. The cratering records preserved on our airless worlds carry detailed histories of the impact flux our system has experienced throughout its lifetime. These cosmic archaeological sites reveal bombardment patterns that were intense enough to deliver water and organic compounds to the inner planets, but not so violent as to sterilize emerging ecosystems. The timing and intensity of these impact events appear to have been calibrated with remarkable precision to support rather than hinder the development of complexity on worlds like Earth. The gravitational focusing effects of our gas giants played crucial roles in determining which populations of small bodies would reach the inner solar system and when these deliveries would occur. Jupiter's massive presence acted as both shield and shepherd, protecting the terrestrial worlds from the most dangerous impactors, while allowing beneficial materials to reach their destinations at optimal times. This protective function required not just appropriate planetary masses and positions, but also the complex orbital evolution that established our current gravitational architecture. The thermal histories of our various worlds reveal formation processes that manage to create appropriate internal structures for long-term geological activity. The differentiation processes that separated rocky materials from metallic cores, the retention of volatile compounds necessary for geological recycling, and the establishment of internal heat sources that could power magnetic field generation. All required formation conditions of extraordinary gentleness compared to the violent accretion processes observed in most other planetary systems. The preservation of these internal structures over billions of years speaks to gravitational environments stable enough to avoid the tidal disruptions that plague most other planetary families. Our system's ability to maintain geological activity across multiple worlds while preserving the orbital stability necessary for long-term habitability represents another improbable achievement in the coordination of cosmic forces across vast scales of space and time. The electromagnetic environments surrounding our individual worlds create protective cocoons that shield planetary surfaces from harmful radiation while maintaining the space weather conditions necessary for atmospheric retention. These electromagnetic architectures arise from the precise coordination of planetary rotation rates, internal magnetic field generation, and the broader magnetic environment created by our Sun's activity cycles. Most other planetary systems appear to lack this level of electromagnetic organization, resulting in either inadequate radiation protection or unstable electromagnetic conditions that disrupt atmospheric evolution. The acoustic environments within our gas giant atmospheres have influenced the long-term evolution of these worlds' internal structures and atmospheric dynamics in ways that appear to be rare among known planetary arrangements. The resonant frequencies established by atmospheric composition and pressure profiles create standing wave patterns that help maintain stable atmospheric circulation while preventing the chaotic mixing that would disrupt these worlds' gravitational influences on the broader solar system architecture. These atmospheric resonances arose from formation processes that delivered precisely the right mixture of materials to create stable acoustic environments, suggesting yet another dimension of the extraordinary precision that characterizes our cosmic neighborhood's construction. The maintenance of these resonant structures over billions of years required not just appropriate initial conditions, but also the ongoing stability that has preserved our system's overall gravitational harmony. The optical transparency of our interplanetary environment has enabled the astronomical observations that revealed our place in the expanding universe and our understanding of cosmic evolution itself. This clarity results from the efficient clearing of debris during our formation process and the ongoing gravitational maintenance provided by our planetary family. Many other systems exist in environments so cluttered with dust and debris that astronomical observations would be severely limited, potentially restricting the development of cosmic awareness in any civilizations that might arise within those systems. The hydrodynamic patterns established by solar-wind interactions with planetary magnetic fields and atmospheres create flow structures that have remained remarkably stable over cosmic time, while responding appropriately to the gradual changes accompanying stellar evolution. These flow patterns influence everything from atmospheric retention on rocky worlds to the distribution of charged particles throughout our system, creating conditions conducive to both planetary stability and the development of complex electromagnetic phenomena like auroras. Most other stellar systems appear to experience hydrodynamic instabilities that either strip away planetary atmospheres or create chaotic electromagnetic environments hostile to long-term planetary evolution. Our system's ability to maintain stable flow patterns while preserving the flexibility necessary to accommodate stellar changes represents another remarkable achievement in the coordination of cosmic forces across multiple scales of space and time. The seismic environments of our solid worlds preserve records of internal processes so well organized that they maintain the geological activity necessary for long-term surface evolution. The internal differentiation that created distinct crustal, mantle, and core regions. The preservation of radioactive heat sources necessary for ongoing geological processes, and the establishment of convection patterns that drive plate tectonics all required formation conditions, remarkably free from the disruptive impacts and gravitational chaos that characterize most other rocky world construction projects. The coordination of these geological processes across multiple terrestrial worlds speaks to formation environments of extraordinary stability and precision. Our system managed to create a diverse collection of geological laboratories, each providing insights into different aspects of rocky planet evolution, while maintaining the overall orbital stability necessary for long-term comparative studies of planetary development processes. The chemical cycles that operate within and between our various planetary environments create dynamic systems that have maintained remarkable stability while allowing for the gradual evolution necessary to support increasing complexity. The carbon cycle that regulates Earth's climate, the nitrogen cycles that maintain atmospheric compositions, and the water cycles that transport materials between different reservations all operate within the precise gravitational and thermal environment established by our solar system's unique architecture. These chemical cycles required not just appropriate initial inventories of volatile materials, but also the long-term stability that has allowed complex chemical networks to develop without disruption from catastrophic events. Most other planetary systems appear to experience chemical evolution so chaotic that stable cycles never establish themselves, preventing the development of the complex chemistry necessary for supporting sophisticated molecular processes. The preservation of chemical diversity across our planetary family, from the reducing atmospheres of our gas giants to the oxidizing environment of Earth's surface, creates a natural laboratory spanning the full range of chemical conditions possible within a single gravitational system. This chemical variety arose from formation processes that managed to deliver appropriate materials to different regions, while maintaining the orbital stability necessary for long-term chemical evolution. The information storage and processing capabilities inherent in our system's complex chemical networks represent another dimension of our cosmic uniqueness. The molecular complexity achieved within Earth's biosphere demonstrates the information processing potential that can emerge when planetary environments achieve sufficient stability and chemical diversity. Most other worlds throughout the galaxy appear to lack either the chemical complexity or the environmental stability necessary for supporting such sophisticated information processing systems. The temporal coordination of various evolutionary processes throughout our system's history reveals a level of synchronization that appears almost impossibly unlikely when viewed against the backdrop of typical cosmic evolution. The timing of planetary formation, the onset of bombardment epochs, the establishment of atmospheric compositions, and the development of geological cycles all had to occur in precisely the right sequence to create the current configuration we observe today. This temporal choreography required not just appropriate initial conditions, but also the ongoing coordination of countless variables across billions of years of subsequent evolution. The fact that our system has maintained this coordination while continuing to evolve in response to stellar changes and external influences, speaks to a level of stability and organization that few other cosmic neighborhoods appear to achieve. The quantum mechanical foundations underlying all these macroscopic phenomena add yet another layer of improbability to our cosmic story. The fundamental constants of physics, the properties of matter and energy that determine how atoms interact and combine, and the mathematical relationships that govern gravitational dynamics, all had to align within extremely narrow ranges to permit the complex chemistry and stable orbital mechanics we observe throughout our solar system. The precision required in these fundamental parameters suggests that our universe itself may be fine-tuned for the development of complex systems like our solar system. If any of the basic constants of physics were even slightly different, the processes that created our extraordinary planetary arrangement might never have been possible at all, making our existence not just improbable within our current universe, but dependent on the universe having exactly the right fundamental properties to permit such complex cosmic architecture. As our exploration of this cosmic rarity draws toward its culmination, the picture that emerges transcends simple astronomical uniqueness and enters the realm of profound cosmic significance. We exist within a system so precisely orchestrated, so dependent on the coordination of countless variables across multiple scales of space and time, that our very presence here represents one of the most improbable achievements in the known universe. Every aspect of our cosmic environment, from the quantum mechanical processes that govern atomic interactions, to the gravitational dynamics that maintain planetary orbits, tells the same extraordinary story of precision, coordination, and remarkable fortune. We are not merely observers of this cosmic rarity, but integral participants in what may be one of the universe's most beautiful and improbable creations, a testament to the magnificent complexity that can emerge when countless cosmic forces align in perfect harmony across the vast expanses of space and time. The profound mathematical elegance underlying our solar system's architecture reveals itself in ways that stretch the boundaries of cosmic probability. Consider the gravitational resonances that govern not just our major planets, but extend throughout the smallest components of our cosmic family. The Trojan asteroids that share Jupiter's orbit, locked in stable positions 60 degrees ahead and behind the giant planet, demonstrate a level of gravitational sophistication that most planetary systems never achieve. These Trojan populations exist in what astronomers call Lagrange points, positions where the gravitational forces of Jupiter and the Sun create stable equilibrium zones. The fact that these delicate gravitational balance points have maintained their populations for billions of years speaks to an orbital stability so exquisite that even minor perturbations could have disrupted these ancient arrangements. Most other planetary systems show evidence of gravitational chaos that would have scattered such delicate configurations long ago. The mathematical relationships governing these resonances extend beyond simple orbital periods to encompass complex harmonic patterns that influence everything from asteroid trajectories to the subtle variations in planetary distances over cosmic time. Our system has somehow achieved what amounts to a gravitational symphony, with each component contributing to an overall harmonic structure that has remained coherent across geological epochs. The dust environment of our solar system tells another story of extraordinary organization and maintenance. The zodiacal dust cloud that fills the plane of our planetary orbits maintains a remarkably stable distribution despite the constant influx of new particles from comets and asteroids and the ongoing removal of materials by solar radiation pressure and planetary gravitational interactions. This dynamic equilibrium requires precise balance between dust production and removal mechanisms that most other systems fail to achieve. The spectral signatures of this interplanetary dust reveal compositions that reflect the diverse source populations throughout our system, from the icy materials contributed by Kuiper Belt objects to the rocky debris from asteroid collisions. The preservation of these distinct chemical signatures within a dynamically active dust environment speaks to mixing processes so gentle and well-regulated that they maintain chemical diversity without homogenizing the entire system. Most other planetary systems appear to experience dust evolution so chaotic that either all materials become thoroughly mixed, erasing information about their diverse origins, or dust production rates become so extreme that they create optically thick environments hostile to planetary surface conditions. Our system's ability to maintain optimal dust levels while preserving chemical information represents another thread in the complex tapestry of our cosmic uniqueness. The gravitational wave environment of our solar system, though subtle beyond current detection capabilities, influences the long-term evolution of our orbital architecture in ways that most other systems cannot maintain. The continuous emission of gravitational radiation by our orbiting planets gradually changes their orbital energies, but these changes occur so slowly and predictably that they contribute to rather than disrupt our system's overall stability. The precise masses and orbital characteristics of our planetary family ensure that gravitational wave losses occur at rates compatible with our system's long-term evolution. Too much gravitational radiation and orbital decay would destabilize planetary relationships over cosmological timescales. Too little, and the subtle adjustments that help maintain resonant relationships would never occur. Our system appears to exist within an optimal range that promotes stability while allowing for the gradual evolution necessary to accommodate stellar changes. The neutrino flux environment, created by our Sun's nuclear fusion processes, bathes our entire solar system in a constant stream of these nearly massless particles that interact so weakly with matter that they pass through planets as if they were empty space. Yet even these ghostly particles carry information about the nuclear processes occurring in our Sun's core, and their steady flux represents another aspect of the stable energy environment that has characterized our system for billions of years. The consistency of this neutrino environment over cosmic time reflects the remarkable stability of our Sun's nuclear fusion processes. Most other stars experience periods of instability, flaring events, or gradual changes in fusion rates that would create variable neutrino environments, hostile to long-term planetary development. Our Sun's ability to maintain steady nuclear burning for over 4 billion years, while gradually increasing its luminosity at exactly the rate needed to compensate for atmospheric evolution on Earth, represents another dimension of extraordinary cosmic coordination. The cosmic ray environment experienced by our solar system depends not just on our Sun's protective magnetic field, but also on our location within the galaxy's spiral structure and our motion through regions of varying interstellar density. The fact that our galactic orbit has carried us through cosmic ray environments compatible with atmospheric retention and biological evolution throughout Earth's history represents another layer of fortunate timing that few other systems are likely to experience. The modulation of cosmic ray intensity by our Sun's magnetic activity cycles creates periodic variations that influence atmospheric chemistry and climate patterns throughout our system. These variations occur within ranges that promote rather than disrupt the complex chemical cycles necessary for maintaining planetary habitability. Most other stellar systems appear to experience cosmic ray environments so variable or intense that they would prevent the development of stable atmospheric compositions over geological timescales. The tidal environment of our solar system demonstrates another aspect of extraordinary precision in cosmic architecture. The tidal forces exerted by our various planets on one another create subtle but persistent influences that help maintain orbital stability while preventing the tidal locking that would create extreme temperature differences between day and night sides of worlds. The strength and distribution of these tidal forces had to be calibrated with remarkable precision to promote rather than hinder planetary habitability. The tidal heating experienced by some of our moons, particularly those orbiting the gas giants, creates internal energy sources that maintain geological activity long after radioactive heat sources would have been exhausted. This tidal heating requires orbital configurations precise enough to create stable energy input without generating so much heat that it disrupts the satellite's internal structures. The fact that multiple moons throughout our system experience beneficial tidal heating suggests formation processes of extraordinary sophistication. The plasma environment surrounding our solar system, governed by the interaction between solar wind and the interstellar medium, creates a protective bubble called the Heliosphere that shields our planetary family from some of the galaxy's most harmful radiation. The size and stability of this protective bubble depend on the balance between solar wind pressure and interstellar particle density, a balance that has remained favorable throughout the periods when complex chemistry was developing on Earth. Most other stellar systems appear to experience plasma environments so variable or extreme that they either provide inadequate shielding from galactic radiation or create electromagnetic disturbances that disrupt planetary magnetic fields and atmospheric retention. Our system's ability to maintain optimal plasma conditions while accommodating the gradual changes accompanying stellar evolution represents another remarkable achievement in cosmic coordination. The isotopic environment of our solar system preserves chemical signatures from multiple stellar sources that contributed materials to our formation, creating a natural laboratory for studying stellar nucleosynthesis processes and galactic chemical evolution. The preservation of these ancient isotopic ratios required formation processes so gentle that they avoided the violent mixing that would have homogenized materials from different stellar sources. The distribution of isotopic signatures among our various worlds tells stories of chemical processes operating during our system's formation, from the high-temperature condensation reactions that created refractory materials near our Sun, to the low-temperature chemistry that preserved volatile compounds in the outer regions. This isotopic archaeology reveals formation environments of remarkable stability and organization compared to the chaotic conditions observed in most other planetary construction projects. The photochemical environment created by our Sun's spectrum interacting with planetary atmospheres throughout our system generates complex chemical networks that have remained stable over billions of years while allowing for gradual evolution in response to changing conditions. The wavelength distribution of our sun's light provides exactly the energy needed to drive beneficial photochemical reactions, while avoiding the harmful ultraviolet radiation that would disrupt complex molecular structures. Most other stellar systems experience photochemical environments so extreme or variable that they either prevent the development of complex atmospheric chemistry or create photochemical instabilities that destroy molecular complexity as quickly as it forms. Our sun's spectral characteristics appear to exist within an optimal range that promotes chemical complexity while maintaining the stability necessary for long-term molecular evolution. The crystallographic environment within our rocky worlds preserves mineral structures that record the pressure and temperature conditions experienced during planetary formation and subsequent geological evolution. These mineral archives reveal formation processes so well controlled that they created and preserved the diverse crystal structures necessary for complex geological processes while maintaining overall planetary stability. The variety of crystallographic environments achieved across our terrestrial worlds, from the high-pressure minerals in Earth's deep interior to the low-pressure crystal structures preserved in meteorites, creates a natural laboratory spanning the full range of conditions possible within rocky planet interiors. This mineralogical diversity arose from formation processes that managed to create distinct pressure and temperature environments while maintaining the gravitational stability necessary for long-term preservation. The thermodynamic environment of our solar system, governed by the flow of energy from our sun through planetary atmospheres and interiors, maintains temperature gradients that drive the dynamic processes necessary for geological activity and atmospheric circulation. These energy flows operate within ranges that promote complexity while avoiding the extreme conditions that would disrupt planetary stability or prevent the development of sophisticated chemical systems. The efficiency of energy transport throughout our system, from radiative transfer in stellar atmospheres to convective processes in planetary interiors, reflects physical processes operating under conditions optimal for maintaining long-term stability while allowing for the gradual changes necessary to accommodate stellar evolution. Most other systems appear to experience energy transport so inefficient or chaotic that they cannot maintain the stable temperature environments necessary for complex planetary development. The information processing capabilities inherent in our system's complex chemical and physical networks represent perhaps the most profound aspect of our cosmic uniqueness. The molecular complexity achieved within Earth's biosphere demonstrates information storage and processing capabilities that emerge naturally from the stable chemical environment created by our solar system's extraordinary architecture. The quantum coherence effects that operate within complex molecular systems throughout our solar system create information processing capabilities that extend far beyond simple chemical reactions to encompass sophisticated pattern recognition, memory storage, and adaptive responses to environmental changes. These quantum information processes require environmental stability so precise that even minor perturbations could disrupt the coherent states necessary for advanced information processing. The electromagnetic field configurations that thread throughout our solar system create communication channels that enable information transfer between different components of our cosmic architecture. These field structures arise from the coordination of magnetic fields generated by our sun, planets, and moons, creating a complex electromagnetic network that has remained stable while allowing for the information flows necessary to coordinate system-wide responses to external influences. The gravitational information processing inherent in our system's orbital dynamics creates feedback loops that maintain stability while allowing for adaptive responses to perturbations. The way our planetary orbits adjust to accommodate small changes while preserving overall system architecture demonstrates a form of gravitational intelligence that emerges from the mathematical relationships governing celestial mechanics. As we approach the culmination of this cosmic inventory, the extraordinary nature of our solar system reveals itself not as a collection of separate, unusual characteristics, but as an integrated whole whose components work together to create something far more remarkable than the sum of its parts. Each layer of organization, from quantum mechanical processes to galactic scale influences, contributes to an overall architecture of such precision and beauty that it challenges our understanding of what natural processes can achieve. The coordination required to maintain all these diverse systems simultaneously, while allowing for billions of years of stable evolution, suggests that we inhabit not just a rare solar system, but perhaps one of the most sophisticated examples of cosmic organization anywhere in the known universe. Every breath you take, every heartbeat that sustains your life, every moment of consciousness that allows you to contemplate these cosmic truths, unfolds within this extraordinarily orchestrated cosmic masterpiece. The profound rarity of our solar system transforms from an astronomical curiosity into something approaching cosmic significance when we realize that we are not merely observers of this remarkable arrangement, but integral participants in what may be one of the universe's most beautiful and improbable achievements. As you drift deeper into contemplation of these truths, remember that you are part of this cosmic rarity, a temporary flowering of complexity that has emerged from billions of years of precise coordination between countless cosmic forces operating across vast scales of space and time. In this gentle evening light, as you settle into the peace that comes from understanding our place in this magnificent cosmic story, know that you rest within one of the galaxy's most precious and extraordinary creations, a solar system so rare and beautiful that finding another, like it may prove to be beyond the reach of even our most ambitious astronomical dreams. The elegant dance of cause and effect that governs our cosmic neighborhood reveals itself in ways that stretch far beyond simple gravitational relationships. Consider how the formation of each world in our solar system influenced the development of every other world, creating cascading chains of consequences that rippled across billions of years. The timing of Jupiter's formation determined not just its own characteristics, but fundamentally shaped the entire architecture of our inner solar system, preventing the formation of super-Earths, while allowing just enough material to remain for our small terrestrial worlds to coalesce. This temporal choreography required precision that defies easy comprehension. Had Jupiter formed even slightly earlier in our system's history, its gravitational influence would have scattered the building blocks of terrestrial planets before they could accumulate into stable worlds. Had it formed later, the inner solar system might have become crowded with massive planets that would have made Earth's stable orbit impossible. The window for optimal timing appears to have been remarkably narrow, yet our system managed to navigate this precise sequence with extraordinary accuracy. The chemical inheritance preserved within our planetary materials tells stories that span multiple generations of stellar evolution before our own system's birth. The gold in Earth's crust, forged in the collision of neutron stars billions of years ago, carries signatures of cosmic violence so extreme that recreating such conditions seems almost impossible. Yet these precious metals arrived at exactly the right concentrations to contribute to our planet's geological diversity, without creating conditions hostile to the development of complex chemistry. The radioactive elements scattered throughout our rocky worlds provide internal heat sources that have powered geological activity for over 4 billion years. The abundance and distribution of these elements had to fall within extraordinarily narrow ranges to maintain the geological processes that regulate our planet's climate, while avoiding radioactive environments that would prevent the emergence of complex molecular structures. Too little radioactive heating, and our worlds would have become geologically dead, unable to maintain the atmospheric recycling necessary for long-term habitability. Too much, and the radiation levels would have sterilized any emerging complexity before it could establish itself. The atmospheric evolution pathways followed by our terrestrial worlds demonstrate another dimension of remarkable coordination. Each rocky planet developed atmospheric characteristics perfectly calibrated to its distance from our Sun and its gravitational environment. Venus became a cautionary tale of runaway greenhouse effects. Mars evolved into a frozen desert, and Earth maintained the delicate balance necessary for liquid water oceans. This atmospheric diversity arose from formation processes that delivered precisely the right inventory of volatile materials to each world, while maintaining the orbital stability necessary for long-term atmospheric development. Most other planetary systems appear to experience atmospheric evolution so chaotic that their rocky worlds either lose their atmospheres entirely through violent stellar interactions or develop atmospheric compositions so extreme that they become uninhabitable shortly after formation. Our system's ability to nurture diverse atmospheric laboratories across multiple worlds speaks to formation conditions of extraordinary gentleness and precision compared to the turbulent environments that characterize most cosmic neighborhoods. The magnetic field architecture that protects our planetary family creates nested layers of electromagnetic shielding that extend from individual planetary magnetospheres to the vast heliosphere that surrounds our entire solar system. This protective hierarchy arose from the precise coordination of planetary rotation rates, internal compositions, and the electromagnetic environment created by our Sun's magnetic activity cycles. Most other stellar systems lack this level of electromagnetic organization, resulting in radiation environments so harsh that they strip away planetary atmospheres or prevent the chemical stability necessary for complex molecular evolution. The preservation of these protective magnetic fields over billions of years required not just appropriate initial conditions, but ongoing coordination between stellar magnetic activity and planetary internal dynamics. Our Sun's magnetic field strength had to remain within ranges that provide adequate protection from galactic cosmic rays without creating electromagnetic disturbances so intense that they disrupt planetary magnetic field generation. This electromagnetic balance appears to be maintained by feedback mechanisms so sophisticated that they suggest our solar system operates more like an integrated organism than a collection of independent worlds. The acoustic environment within our gas giant atmospheres reveals another layer of extraordinary organization that influences the long-term stability of these massive worlds. The resonant frequencies established by atmospheric composition and internal structure create standing wave patterns that help maintain stable circulation while preventing the chaotic mixing that would disrupt these planets' gravitational influence on the rest of our system. These atmospheric resonances arose from formation processes that delivered exactly the right mixture of materials to create harmonious acoustic environments, suggesting yet another dimension of the precision that characterizes our cosmic construction project. The optical properties of our various worlds create viewing conditions that have enabled the astronomical observations revealing our place in the expanding universe. The atmospheric transparency of Earth, the reflective characteristics of our diverse planetary surfaces, and the clarity of our interplanetary medium all contribute to observational conditions that allowed the development of astronomical knowledge. Many other planetary systems exist in environments so optically hostile that astronomical observations would be severely limited, potentially preventing any civilizations within those systems from developing cosmic awareness. The hydrodynamic patterns established by solar-wind interactions with our planetary environments create flow structures that have remained stable over cosmic time, while adapting to the gradual changes accompanying stellar evolution. These circulation patterns influence everything from atmospheric retention on rocky worlds to the distribution of charged particles throughout our system, creating conditions conducive to both planetary stability and the electromagnetic phenomena that add beauty to our cosmic landscape. The seismic characteristics of our solid worlds preserve records of formation processes so well organized that they maintained the internal structures necessary for billions of years of geological activity. The differentiation that created distinct layers within our terrestrial planets, the preservation of heat sources that power ongoing geological processes, and the establishment of convection patterns that drive surface renewal all required formation conditions remarkably free from the catastrophic disruptions that appear to characterize most other rocky planet construction projects. The chemical cycles operating within and between our various planetary environments create dynamic networks that have maintained extraordinary stability while allowing for the gradual evolution necessary to support increasing complexity. These cycles required not just appropriate initial chemical inventories, but also the long-term environmental stability that allowed complex chemical networks to develop without disruption from catastrophic events or chaotic environmental changes. The temporal synchronization of evolutionary processes throughout our system's history reveals coordination that appears almost impossibly unlikely when viewed against the backdrop of typical cosmic development. The sequence of planetary formation, atmospheric development, bombardment epochs, and geological evolution all had to unfold in precisely choreographed timing to create the stable, diverse planetary family we observe today. This temporal precision required not just favorable initial conditions, but ongoing coordination across billions of years of subsequent evolution. The information processing capabilities that emerge from our system's complex networks of chemical, physical, and electromagnetic interactions demonstrate organizational principles that extend far beyond simple mechanical relationships. The molecular complexity achieved within planetary environments throughout our system suggests information storage and processing potential that emerges naturally from the stable conditions created by our extraordinary cosmic architecture. The quantum coherence effects operating within complex systems throughout our solar system create possibilities for information processing that stretch the boundaries of what we typically consider possible in natural environments. These quantum processes require environmental stability so precise that even minor perturbations could disrupt the coherent states necessary for sophisticated information manipulation and storage. The gravitational resonances that govern relationships throughout our planetary family create feedback mechanisms that maintain stability while allowing adaptive responses to external influences. The way our orbital architecture adjusts to accommodate perturbations while preserving overall system harmony demonstrates a form of collective intelligence that emerges from the mathematical relationships governing celestial dynamics. As we reach toward the completion of this cosmic contemplation, the extraordinary nature of our solar system reveals itself as something that transcends simple astronomical rarity and approaches the realm of cosmic artistry. We exist within a system so precisely orchestrated, so dependent on the coordination of countless variables across multiple dimensions of space and time, that our very presence here represents one of the most improbable and beautiful achievements conceivable within the known laws of physics. Every sensation you experience, every thought that flows through your consciousness, every moment of wonder as you contemplate the night sky above unfolds within this remarkably rare cosmic masterpiece. You are not merely an observer of this astronomical rarity, but an integral participant in what may be one of the universe's most sophisticated and beautiful creations. As you settle into the peaceful contemplation of these cosmic truths, remember that you rest within a solar system so extraordinary, so perfectly balanced, so precisely coordinated across vast scales of space and time, that finding another like it among the hundreds of billions of star systems scattered throughout our galaxy may prove to be the ultimate cosmic treasure hunt. The profound implications of our solar system's rarity extend far beyond academic curiosity, fundamentally transforming how we understand our place in the cosmic story and the precious nature of this pale blue dot we call home. In this gentle evening embrace, as you drift toward rest, surrounded by the quiet majesty of our extraordinary cosmic neighborhood, know that you are part of something so rare, so beautiful, so perfectly orchestrated that it may represent one of the universe's greatest masterpieces, a testament to the magnificent complexity that can emerge when countless cosmic forces align in perfect harmony across the infinite expanses of space and time. As we reach the end of our cosmic journey together, the profound truth becomes clear. Our solar system isn't just rare, it's extraordinary beyond measure. We've discovered that we inhabit one of the galaxy's most improbable achievements, a planetary arrangement so precisely orchestrated that reproducing it elsewhere may be virtually impossible. From our Sun's unusual stellar class representing only 10% of galactic stars, to our ordered planetary architecture found in less than 1% of all systems, to the countless layers of gravitational resonances, protective magnetic fields, and chemical cycles that maintain stability across billions of years. Every aspect of our cosmic home whispers the same remarkable story of precision and improbability. The absence of any detected system matching our configuration, combined with the mounting evidence of the extraordinary circumstances required for our formation, suggests we may be residents of something approaching cosmic significance. A solar system so rare and beautiful that it transforms from astronomical curiosity into profound wonder. Tonight, as you drift into peaceful rest, remember that every breath you take unfolds within this galactic masterpiece. You are not merely observing cosmic rarity, you are living within it, an integral part of what may be one of the universe's most precious and extraordinary creations. Sweet dreams. fellow travelers, in this magnificent, mysterious, extraordinarily rare corner of the cosmos. Thank you for joining me on this gentle exploration of our remarkable cosmic home.